All right. Continuing with acids and bases, we're going to talk about the autoionization of water. We've seen in a couple of previous examples that water is amphoteric, meaning it can act as a base, it can act as an acid. And in any sample of water, two molecules of water will actually react. And form the hydronium ion and the hydroxide ion. Now this is a very small amount, but it is referred to as the autoionization of water. And we'll see that this has an impact on how we do calculations to determine different components of an acid-base aqueous system. The equilibrium expression for the process is, here's another K, okay, Kc, general equilibrium constant, is equal to the concentration of the hydronium times the concentration of the hydroxide. These, of course, are in mole per decimeters cubed. We represent it using the ion product constant Kw. At 25 degrees, Kw is 1 times 10 to the negative 14th. This is important to remember. Okay, you should memorize that number. You should memorize that it is the concentration of the hydronium times the concentration of the hydroxide ion. Okay. So how would we calculate the values of H plus and OH in a neutral solution? You would do this just like you would any equilibrium problem. As seen previously, we know that two molecules of water form an equilibrium with the hydronium ion and the hydroxide, oops, I don't need that, hydroxide ion. The expression for that equilibrium, this is the Kw, is the concentration of the hydronium times the concentration of the hydroxide. Remember that this and this are used interchangeably, they mean the same thing. So, if I set up an ice table, I'm going to redo this real quick, sorry. Set up an ice table. Theoretically, well, water doesn't really have a concentration because it doesn't enter into here. Initially, let's say that we don't have any of those formed. When the water ionizes, I'm going to get equal amounts of the hydronium and the hydroxide. So plugging them into this Kw, remember from before, what is the value of Kw? 1 times 10 to the negative 14th is equal to x squared. So x, which is equal to the concentration of the hydronium and the concentration of the hydroxide, is equal to 1 times 10 to the negative 7. If you take the pH of that solution, remember pH is equal to the negative log of the hydronium concentration, we would get 7. Okay, we will let you do these, bring these into class, calculating the concentration of the hydronium and the hydroxide in those two solutions. And let's go on and talk about pH. I knew I threw that at you just momentarily ago, but remember, pH is defined as the negative base 10 log of the concentration of the hydronium ion. And there's the equation. So in pure water, as we've just seen, concentration of the hydronium is 1 times 10 to the negative 7. Therefore, in pure water, the pH is 7. If the acid has a higher concentration than pure water, its pH will be less than 7. If it has a lower than pure water, lower concentration of the hydronium, then its pH is greater than 7. And as you hopefully know, this is termed acidic, and this is termed a basic solution. I will let you do the calculations, and we will go over those in class. Here is just a graph showing some relative pHs of common substances. We should have also done this as a lab in class. The P, that P really just means negative base 10 log of whatever quantity we're talking about. Usually the one that most people are familiar with is pH, but we can use that P, meaning the negative log, for a number of different things. pOH, we can also take a P of a K, of an equilibrium constant, and it is just the negative log of that Kw. I don't know what happened to my symbols. This should be equals. This should be equals. Okay, so pKw, this P just means negative log of. Negative log of whatever the quantity is that's mentioned following it. Okay, we know that the two concentrations in the Kw expression is 1 times 10 to the negative 14th. If we take the negative log of all of those things, it would be equal to 14. In other words, oops, sorry. In other words, pH and pOH is equal to 14. This is an important relationship to know. Hence, memorize that. Okay, important relationship to know. Okay. How do we measure pH? There's a number of different ways. If we really need a just a is it acid, is it base, we can use things called indicators. Litmus paper. Red paper turns blue for pHs at 8 or above, and blue litmus turns red for pHs at about 5 or below. I always remember blue for litmus is equal to base, and this is just for litmus paper. Okay. The trend may hold true for other indicators. I'm not sure if that's a reliable rule of thumb. All right, so you can also use indicators, and we will hopefully do some experiments with that as well. We also use a pH meter. We've used these last year, so we'll be using those again. Okay. Strong acids, there are 7 of them. You need to memorize those. Okay, they are strong electrolytes, exist totally as ions in aqueous solution. If that acid has only 1 proton, meaning it is monoprotic, hydrochloric, hydrobromic, hydroiodic, nitric, chloric, and perchloric are all monoprotic. I only get 1 hydrogen. For those monoprotic strong acids, the concentration of the hydronium is equal to the concentration of the acid because it fully ionizes. Okay. Strong bases, soluble hydroxides, alkali metals, heavier alkaline earth hydroxides. Again, those substances dissociate completely in an aqueous solution. Be aware, though, that your concentration of the hydroxide is going to be dependent on whether I have an alkali metal or an alkali earth metal. Because remember, calcium hydroxide has 2 hydroxides in the formula. So when it fully dissociates, I get the calcium ion and 2 hydroxides. So be aware of that when you are determining the concentration. Next, we will talk about weak acids and bases in the next screencast.